Hey everyone. So, yeah, I'm Hila, and I am a Chief Strategy Officer at Firefly.ai, which basically means that I'm the only non-data science person in a startup of very smart people. I'd like to consider it as my competitive advantage because I get to challenge our researchers in building an automatic system that even data citizens like me can use. Or basically, I get to give them a reality check. I'm the normal people, right? And yes, I'm here to talk about winning Kaggle in 30 minutes. Because I'm a business person, I love fast delivery, I love measurable KPIs, and I was very excited when a new researcher joined our startup and decided to try our system. Short hour later, he produced a winning result. How did he do it? We'll talk about it later on. But the question is, the real one, who cares? Who really cares about winning Kaggle? So if I can see a show of hands, how many people here are being measured at their workplace by winning public challenges? Okay. How many, putting SK aside, are trying to teach their model to differentiate a cat from a dog from a muffin? Do you know this picture? Okay. How many are here because their companies cannot afford to lose their competitive edge? That's much better. Not enough show of hands. I hope your companies are not just wasting their time. But rightfully so, I know I'm preaching to the choir here in this room, but AI is disruptive. It's going to change industries. If we think AI is going to only change few industries in some cases, I think we are wrong. I think that looking back in history, we can compare it to the printing revolution. You know, the printing revolution created an impact that is much more than just, let's say, changing the book writing industry, right? In fact, when I was looking for this image, I found a really nice summary by SUNY University on the printing revolution impact on society and in general, and I felt a déjà vu. If you read through these lines, a community of scientists that bringing together a scientific revolution, making things more consistent in a way that it changed the way knowledge flows to alter structure of society. To me, that's very exciting, and this is why I'm taking active part in this process. But if we come back to the future, our future, I'd like to propose two types of applied machine learning. And if someone noticed that I'm using machine learning instead of AI, as I used before, then that's inspired by Dr. Vivian Ming, who said, AI is when you talk to investors, machine learning is when you talk to scientists. So here we go. This division is the way I view the world. One is trying to mimic human ability. We know how to tell a dog from a muffin, right? But teaching systems, machines to do that will gain us the benefits of machines: faster, cheaper, more consistent. That's one part. The other part is actually to improve on human ability, especially in the computation part of the things, right? Being able to make decisions better than what humans can possibly factor in. And this is the part that I'd like to focus on. I call it superpowering our decisions. And which decisions can we superpower? Well, any decisions. But here are a few very common use cases: to lend or not to lend, right? Credit risk. When should I service the equipment? Predictive maintenance, I think someone already mentioned that today. Is she about to leave me? What can I do to make her stay? Customer churn. Is this a cyber attack, or are you just happy to see me? Right? And last, in this case, is there someone on the train tracks, or is it just a cloud? If this one is not as straightforward as the others, that's good. We'll talk about it later. Sounds great, many decisions. Let's do machine learning. Great, reality check, right? Kaggle survey and many other surveys are saying that there are challenges when scientists are facing in their work. The great opening session mentioned few of them, starting from the three orange ones: lack of data science talent, lack of management support, and lack of clear question to ask. I'd like to, something is going on here. There is a top big elephant in the room, which was dirty data. I'm not going to address it directly, although we're going to touch it. There are hundreds of teams across the world trying to solve the dirty data challenge. But I'm not going to focus on those issues right now. I'm going to focus on the other three, starting from bottom up. So lack of clear question to ask. I just demonstrated how you can put your use case in a business question way. I know that in many boardrooms and management meetings, there is this notion of, we have all this data. There must be something we can do with it. Let's just give it to the data scientist, and then nothing happens, right? I'd like to propose a more pragmatic approach, think very much in line with the first session. 3 steps. Step number 1, find the question behind the daily decisions your business make as its core, to lend or not to lend. Or, for example, with an online retailer, how do I price my product on Amazon? What is the other questions behind it? What's going to be the demand for that product? And what's the competition is going to do, right? Then evaluate the impact of improving the decision. What does it mean to improve the decision? Make it faster or make it more accurate. In our online retailer example, if I price it better, I'm going to lose less deals to the competition. I'm going to leave less money on the table. And I'm also going to manage my inventory better, so I'm going to pay less storage for that, okay? Clear ROI here. So now go fetch the data. And the data can start being dirty or just pulling from different places. It doesn't need to be all organized before you prove your point. First, prove the point and go to the management, which leads me to lack of management support, or the way I like to call it, what do executives want? So executives like ROI, they like business value, not so much research project. You know what an executive like me hears when she hears research project? I hear, I don't know how long it's going to take. I don't know how much it's going to cost me, and I don't know if it's even going to succeed, right? Let's say it did succeed. Now, they want an easy way to scale it up. They don't want to hear, oh, great, let's do another research project. No. So what we want to do when we talk to executives, we want to be very focused on the business. We want to have a fast and cost-effective way to experiment. And I think Adrian touched on building those frameworks that allow you to deliver fast and then scale up on the operation. This is kind of the framework. And the other top reason there was lack of data science talent. I don't need to talk to you about it. But I think we need to let data scientists focus on the content and not on the technicality. If I'm drawing back on the printing revolution, I think that we need to find the printing machine. We don't have a printing machine for data science project yet. And in this way, we can allow the data scientists to become the experts of their domain rather than the technicians of the data science. And this all brings me to AutoML. How many here know about AutoML and heard this before? Okay, few, great. So AutoML is a growing field within the machine learning research. Basically, it means it is applying machine learning on machine learning, and it's trying to automatically build hundreds of models in parallel to find the best model, okay? From the big process of what it takes to do a data science or a machine learning process, it focuses on the part where you research for the right algorithms, you apply pre-processing on the data, you optimize for your hyperparameters, you select your metrics, and then you get the best model. A model can be constructed of a single algorithm, a single model, or an ensemble of models, and we'll talk a little bit more about it. There are several open source tools and some paid options in the industry. AutoWeka and AutoScaLearn are open source libraries that are available, and you can download them and try them on. There are also some paid options. Some are very specific. For example, Google Cloud AutoML is very specific for vision, okay? And I do urge you to try and experiment with those libraries. When you do that, there are some things that you want to look for. You want to look for their algorithms availability. So if you are trying to build models automatically, the algorithms are your building blocks. So you're only as good as the algorithms availability that they offer. You want to make sure that they have good variety and that it's being up to date frequently enough. You want to see the pre-processing capabilities. You all mentioned that the pre-processing is a huge part of the heavy lifting work that goes into a project. So the more automation, the better. I think Adrian mentioned, and I couldn't agree more, that sometimes your model is only as good as your pre-processing and more even important than the right algorithm. You want to look for the search methods. Now, the search method is specific for AutoML, the way it searches on the hyperparameter space for the right model and the right algorithms. There are several methods. I think you can read some on some of it. Some of it is grid search or random search. But I think there is an agreement that Bayesian optimization is the most successful one. And even within the Bayesian optimization, there are techniques to make it faster and better, like applying meta-learning. I want to show you a short movie that illustrates how that search is being done. What you're going to see, let's see if it works. Okay. So what you're going to see is you're going to see what we call on the movie workers. You're going to see computation units running in the search and trying different estimators, algorithms with different parameters and producing results. This is what it looks like.
Here's how Firefly automatically builds.
Here. So I'm going to skip the marketing thing, but show you that it's running. Here it tries neural network. Here it's trying XGBoost, random forest. Red is bad, green is okay, and blue is the best. And it's just trying based on whatever metrics you gave it to figure out the best models. At the end of the process, it will select the best ensemble of models to produce the best model. Okay? It's almost done. I'm going to skip it. So when you put all of it together in a platform, there are two main modules or workflows. One is your lab. This is where you build the models, you run your experiments, and the other is the predict, where you actually put the models to work, okay? At the lab, you obviously connect to your data. You do have, as a data scientist, to select what type of machine learning task this is. Are we talking about classification, recommendation, time series, etc.? I didn't mention it before, but when you check your libraries, it's also a factor. Some libraries are focused only on one task, others are focused on provide more variety of tasks. Then the magic happens, right? This running around, guided by meta-learning, a lot of pre-processing, so a lot of automatic data cleaning, imputation, embedding, stacking, all of that, okay? The algorithm selection, and then generating a solution, an ensemble, a model made out of an ensemble with very clear documentation of it. I'm gonna pause it for a second because I don't know how many of you are facing explainability challenges, trying to explain what the model is actually doing, right? So we...
I have a question. Like when you assemble so many models, like you said, you have the new, it might give you like top 10, top 20, and you ensemble.
Mm-hmm.
And you have models ranging from logistic regression to, let's say, deep learning, and you ensemble them. And then, yeah, I mean, it's an extension of what you're about.
Absolutely. Yeah, I'm going to touch on that a little bit also later on, but you can set your preference. Do you prefer to have very high accuracy or a simple explainable model? Okay, there is some of a balance between those two. Sometimes you also get a simple and accurate model, but yes, you're right. The more complex it is, the harder it is to explain. And this is why when you're applying AutoML, it's also important to get a very clear understanding of what happened in that automatic process. Okay, so you will be able to explain it to your stakeholders. And then you have a model. Hopefully, the model is part of a successful project that is being put in production. And then the question is, what type of prediction do you need? Do you need it on real time or in a batch process? Do you want to use it in an API? Do you want to export the model and implement it there? Those are different options that can be available. So this is a little bit of the background behind it. Now let's see how AutoML is being used in real life cases. And here I'm going to touch on the clouds and the train wrecks, and also connect to the Safe City project. So this, can you see this image? Do you see what it is? Okay, so this is a case of an existing Homeland Security project, part of a Safe City project. Okay, this is based on video analytics, where the video analytics is rule-based, and it's triggering an alert saying there is something on the tracks. The problem is, it also says there is something on the tracks when there is a cloud, or a shadow, or something that is just not a true alert. To the point that there are so many false alarms that the control room staff just stopped using it. It became unusable. Then came the idea of applying machine learning to try and filter out the false alarms. Okay, so we're talking about more of a legacy rule-based system that we're applying machine learning on top of it. The input to the machine learning model was the video analytics results. So if you see here, those lines, those are made automatically by the video analytics. We get them as numerical data. Okay, that is being fed into the machine learning model. Now we face a second challenge. having enough true cases to simulate true accidents, okay? So we have a lot of false alarms, but the anomaly is so rare that we didn't have enough training material for the model to train on real cases. And this is what this picture is from. This is a simulation of real people on trucks. So we'll have the training data for the model, okay? That was used for the actual model. A second challenge was trying to build a generic model for all the cameras is almost impossible because it will require so much data that was just not available. This city just didn't have all this data. This is where AutoML was very useful because we are able to produce different models per location, per camera. In this case, the training data needed is actually much smaller and manageable, okay? So this is the approach that was taken. It reduced off the batch, reduction of 90% in the false alarm. Basically, it put the operational system back into business. They started using it again. And we just got results that it keeps improving because it keeps learning. So the accuracy is going up, and that's great. Another case study. Just to give you a glimpse of what it looks like when we build the model. So what you see here is feature sensitivity analysis on the top by two methods. And I don't know if you can read it, but you see that the direction is very important. So top, bottom, left, right, and you see it's very location sensitive. Okay, and that's why it needed to be very localized. This is a visual report.
You're reducing your false alarms by 90%. And how much efficiency are you losing? In a case like that where you're trying to prevent someone from being hit by a train, I would think if you lose half your efficiency, that's not good.
So you are very right, and we cannot. So part of the cost metrics, if you want, was such that we cannot lose real case. So that was our. We have multiple ways of management, and we did not lose any true case. Okay, that was the. You see here the multiple models that were built in the process, and then this was the chosen ensemble. Okay, and from the report you can see that it involved extra tree and decision tree and anomaly GMM, etc. In this case, we can allow for a very complex model because no human needs to understand it. Those are security experts; they're good with that. Okay. Another case was of cybersecurity. This case is based on network data to identify cybersecurity attack. Again, it's a very dynamic environment. In this case, every organization has their own network security behavior, so it needs to build a model per organization. It needs to be very fast. It needs to be very accurate. The cost of shutting down network for an organization is huge. So when a system like this is alerting, and then the security officer of a company says, okay, no emails for today, that's not an easy decision to make, okay? So it needs to be very simple. So I don't know if you see here, look at this. Look how many models the system tried. Tons of models, hundreds of models, but at the end, it only selected one model. This is the darker line here, because it was really important that we can clearly say why this system needs to be shut down, okay? And there are some other features here that I'm not going to discuss. I'm running out of time, and I did want to talk about the Kaggle competition. So by now, you can probably understand that there was no magic to it. This new hire was sent like any other new hire to learn our system. He chose to do it by downloading a Kaggle competition. It was a Mercedes-Benz reliability prediction. This competition was already closed, but still you can see here you could submit your result. He downloaded the data, he uploaded it to the system. He didn't do any pre-processing. It was just to learn how the system works, which buttons to click. He clicked, and received a winning score. So here the leader had a 0.0555, and he had a 0.5579. It's a nice range above the former leader. It wasn't our objective to build a Kaggle winning system. Our objective was to win an ROI winning system, but it happened to be accurate. We wanted to make sure it wasn't a mistake, so we sent another one to download another data set. This one, it was for Santander Bank to predict customer satisfaction. This time, by the way, the winner had 0.829, and our result was 0.834. The point spread between this result and this result is like the point spread between the former leading one and the 270 something. So it's really huge spread point. So to summarize, I think AutoML can become our printing machine. It can really help us put more things in production if you'd like. And it can also be very accurate. It's not necessarily compromising your accuracy. What it cannot do, it cannot learn how to ask the right business question. It cannot learn how to convey to your organization and make it a reality. And this is where we need really strong data scientists. Thank you.
All right.